Okay, am I audible?
Yes, sir.
Yes.
Yeah. Okay, so let's wait for 2 minutes. So how is your exams, internal, for this subject? I think you got the scores. Did you get your scores? Deep, Milan,
Yes,
Vijay?
sir.
Yeah, nice. Okay, so
Hello.
yes. Yeah, okay, I think it's time we can start up. And don't give your attendance here. So it's low because you did not study, na? You did not go through the slides. That's why it is low. So try to go through the notes and slides, and you will be having a better chance. So let's start. It's already 3:05. Okay, so this is unit 2. This is unit 2. So unit 2 is consisting of DC motor drives. So first we will go to the basics and then we will go to the advanced features. So unit 1 was all about what types of loads are
Sir, I
there.
think we haven't completed unit module 1 completely.
Yes, module 1 is complete because thermal modeling was done in a separate class. I request you to go through the recording lecture, right? So I think lecture 10 was there. So what I will do, I will include that lecture 10 within that drive link, then you will be able to access it. Is it
Sir,
okay?
thermal modeling was I didn't attend the class, right?
Yes, so you have the recording and I will also put the recording within the
No,
drive
I
link.
mean, when did that happen? Like, I should be attending the class. I attend every class. Like, when did that happen, sir?
Okay, Deep, do one thing, go through the recording. If there are any doubts, just come up to me. Is that okay?
Okay, sir.
If it is self-explanatory, then it is good. If it is not, just come to my cabin, then it will be fine, right? So everyone who missed that class, please go through the recording. If you have a problem, then we will hold another class to solve all the issues. Okay. So let's today start with a fresh class on this module 2. So module unit 1, that was module 1, was actually on the types of loads, whether the drives are stable or not. So drive stability was there and all. And now module 2 will deal with DC motor drives. That is the drives concerned with the running of DC motors. See, any drives, whether it is AC or DC, will have to perform 3 things in common. Can you tell those 3 things?
Sir, control, I mean,
Yeah, what is the function of the drive? First, you have to know it.
control, sir, I think.
The control means what? See, control means something, na? Say if you have an
Control
electric,
speed.
say if you go
Torque and speed.
to the Bhubaneswar area, there are Honda electric car showroom, electric vehicle showroom has already come up, right? So if you take that thing, what is your aim now? Your aim will be to start the vehicle, right? First of all, you will start it, then you will control the speed, and then you will brake it when you are near about to reach your home. Is it not so?
Yes, sir.
So first of all, your work will be to start. So starting, then speed control,
Acceleration, deceleration.
and then finally braking, right? So every drive has to make these 3 things happen. This is the ultimate aim of any drive. One has to start Then speed control means acceleration or deacceleration, and then you have to brake, right? Just a second, just a second. Yeah, hello. Yeah, so the first of all work is to start the vehicle. Then once it is started, for starting you need a very high torque. I think we are aware of this fan. We are aware of this thing that in order to start a vehicle, you need the highest amount of torque. So starting torque is the highest. Starting torque is the highest now. So here the power flow goes from the source to the load, right? And then you have to have a speed control thing. The speed control is to adjust the speed in between the 0 and max. And then finally, when you will be reaching towards the home, you have to again brake that thing, right? So braking, we will see how many types of braking are there. What are the types of speed control means methods of speed control. How will you control? Can you imagine a electric scooter you bought and it only has a starting key and it does not have any speed controller? How would the journey be? Means once you switch it on, it will run on its full speed. And once you switch it off, it will slowly go down. So can you think of such a thing? Would you like to buy that vehicle?
So it depends upon application.
No, I'm telling you specifically this electric scooter that is right now in news. So
No, sir.
just so if you have a button like on off switch on button, you have to just switch it on and it will start running at the full speed. And then when you reach home, it will just switch it off. It will slowly go down. So you cannot think of such a thing, right? Because you do not have a control over the speed. So in order to have a control over speed, what you need some methods to control the speed of the machine, right? And then finally, when you are about to reach the home, so what you will do, you will try to brake it. Now braking will be of 4 types, right? So one type is what? Physical mechanical brakes, simple, right? Then dynamic braking, we will go to it again, don't worry. Then plugging, and then finally regenerative braking, right? So we'll slowly go to all of them one by one. So this was just a hint on what we'll be doing. Okay, so let us see what are the types of DC motors that are available in the market. So these types of motors are actually having brushes. So their popularity went down and down with time, and nowadays they are hardly found. Uh, you have to again go and buy these things. You won't be able to see DC motors so much easily, right? Because their brushes are a big problem. They need to change the brushes. Yet the DC machines are very much linear machines for which they are used in many critical applications where a very good amount of control is required. So first of all, we will have the sorry, separately excited machine. So separately excited means this coil, this field coil is separately excited through another separate source, right? Then we have called the shunt machine. So this shunt machine is having its power supply connected in parallel with the armature supply. So can you see that this field, which was earlier having a separate DC supply, it was very hectic to find another separate DC supply, right? Because once you get this 220-volt DC, say after rectification, then again you have to attach another rectifier and see to it. So people, what they did, they kept this winding in parallel. So this became the shunt DC machine. Machine means it can be, see this word machine means it can be either motor or generator, right? But we are studying electric drives for which the motoring action is specifically seen. But during the regenerative braking, this machine will become a generator itself, right? So in general, we will call it machine. As per use, we will call it either motor or generator. Then comes the series machine. This is a well-known thing. And can you tell me where is it basically used for in our normal day-to-day life? Series machine. Its torque is proportional to I square. So just think of it, I square. Whatever current you give, by the square of that, the torque will be.
Yes, answer.
Maya, are you back home?
The mixer?
Yes.
No, sir.
So tell me, where is the latest
The
application?
scooty and bikes.
Scooty and bikes in where? Scooty and bikes where?
Electric scooty and electric bikes.
No, 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 no. In normal IC engine based bikes and scooters also, this series motor is
For
used. Where
starting,
is
sir.
it
For
used?
starting.
Yeah,
For
for
starting.
self starting.
Oh yes, sir.
It
Because
is
very hard
just
of this
for
part.
some 4 to 5 seconds. It is just for 4 to 5 seconds you have to keep this motor on. Not even 4 to 5 seconds, 1 or 2 seconds might be. If the battery goes off, someone keeps it on for 4 to 5 seconds also. Right. So this thing is only on for 4 to 5 seconds maximum in a series DC motor. So this provides a very high amount of torque, which is basically used to start the machine, which is basically used to start the say vehicle, or in case of cranes also it is used, as you saw earlier. In case of cranes also it is used just to pick up a very high amount of load. That is used in short-term duty, short-term duty. Right. So once it is used and then again it is fall flat. Right. So this is a very popular motor as far as short-term duty is concerned. For the running load, the shunt machine is used. Actually, these are the two motors which was used in earlier tractions, means electric tractions. Nowadays, these are not used. Some trains it is there still, but nowadays it is not used. And so cumulative compound is a combination of a series DC machine and a shunt DC machine, so that we can have both the characteristics. During the initial time, this will act as a series DC machine so as to pick up the load. Once the load has attained a particular speed, then this shunt winding will be on. So that's the thing. Some people might be thinking that, okay, what about BLDC motor? That's also a DC motor, right? Is it not so? The answer is no. BLDC motor is an AC motor, not a DC motor, right? So later you will understand why. Okay, so basic configurations of DC motor drives. So basically it can be single phase or three phase, right? From where is single phase and three phase coming?
From mains grid.
So you have a socket, right? This socket can either provide you single phase or three phase, right? So if you take out the thing from single phase, what you will call? One configuration is that for separately excited machine, you take out this supply, 5 ampere supply, and then put it into a what? You put it here. And this is what? Control rectifier. Do you remember the control rectifier? What a control rectifier is? Let me draw it again.
Thyristor.
Yes. Thyristor based rectifier,
Cycloconvert.
not cycloconverter. Rectifier. Do you remember this?
Yes, sir.
This was the RLE load. And what was the average voltage here? The VDC voltage was
Division by
2 Vm by
division by
pi, then
cos alpha, cos alpha.
cos alpha, right? So as for the alpha, it would become a rectifier or an inverter. If alpha was greater than 90, it was inverting, right? So here we will consider it this control. We can have a semi-controlled or a fully controlled. If the power rating is less, we can go for semi-controlled. If the power rating is very high, we can go for fully controlled,
Yes.
right?
Correct.
So, okay, sorry. And what about this field winding? How will you supply the field winding? In a separately excited DC motor, you need a constant supply of DC volts, say 230 volt DC, right? So what you will do, you will take a simple rectifier, uncontrolled rectifier, right? You can take an uncontrolled rectifier at a very low cost if you just want armature control, or you can take a fully controlled rectifier if your budget is a bit higher, right? So you take a diode bridge or a controlled rectifier. Diode bridge is actually uncontrolled rectifier. So do you know the circuit diagram of diode bridge rectifier? This is the simple rectifier. So basically saying, I will clear it up. So basically saying you have a DC motor and you want to supply, you want to control it. So what you will do, as far you are controlling it from the grid power supply. So you will connect this time, and you also have a this type of power supply. So where will you power this up from? The field F. So first of all, you will try to power this motor up from a what, AC power supply, right? So when you try to power up from the supply, if it is uncontrolled, it will keep on start to run. It will not happen. So you will need a control rectifier. Either it can be semi-controlled. This is the symmetrical one. Do you remember this?
Yes, sir.
Or it can be a fully controlled if the power level is high. So in that case, it will be 2 Vm by pi cos alpha is equals to VDC, right? And the current cannot reverse through this, right? And whatever the field supply, you will take a AC supply. You will take AC supply and give it to this point. So this can be AC supply, right? So this is AC supply, this is the DC supply output. This is the bridge, and this can be uncontrolled or it can be semi-controlled or can be fully controlled also. Is it not so? But which one will be cheap if you want to go for only the armature side control? If you want to go for only this side control, armature side, then what would be cheap? To have an uncontrolled rectifier on this part. Is it not so? See, what is the cost of a diode? The cost of a diode would be in the range of around 10 rupees per unit. So four diodes are 40 rupees, right? And what will be the cost of a thyristor? Minimum thyristor locally would be around 75 rupees. Into 4 would be 300 rupees. I think I'm right. So which one would be cheaper option?
Diodes.
Diode.
So diodes. So just go for some 4 uncontrolled diodes and supply this with full amount of voltage, right? So it is done for you. I myself has done this several times. So it is good, right? Now there are two ways to control it. We will later see to it. And here you can add another bridge if it is three phase. Is it not so? If it is single phase, then then only this much. If it is single phase, then this also gets added up. Hope you remember it.
Yes, sir.
Yeah. So it can be either single phase or three phase drives, right? And DC-DC drives can also be run from a DC supply also. So in that case, what would be the thing? First of all, get the DC. DC means if you want all the four quadrant operation, you can go for maximum four quadrant operation, right? Or if you want one quadrant or second quadrant, right? So you can go for class C choppers also or four quadrant chopper, right?
Yes.
So you get a diode rectifier that is uncontrolled at 40 rupees for the four diodes, and then employ a MOSFET or IGBT based DC-DC converter. Wouldn't it be nice?
Sir, again, sir, can you?
Say you have two options, right? Here is a DC motor, and you have two options. First of all, you can employ a 10 rupees per item of diode to get a DC supply. Very easy to do it, right? Then you add a capacitor, and then you add a what? Four
Motor.
quadrant chopper? No, four quadrant.
Oh,
Say class C chopper you want.
hmm.
Class C chopper would have an inbuilt diode within itself, so no issue with that. So is this configuration good? This is what?
Hmm.
It's a class C chopper, right?
Mm.
And this is what? Uncontrolled diode, uncontrolled bridge, diode bridge. Is it not
Yes,
so?
sir.
So
Yes,
if you
sir.
want to make a product, you have to always search for the what? You have to always search for the least cost of the
Cheaper
product,
options. Cheaper options.
cheaper options. If your product is say a big amount, then people would not try to buy it, right? So either you can have four thyristors or you can have two MOSFETs. Say if you want to have four thyristors, SCRs, each one will be costing you around 75 rupees, into four pieces would be 300 rupees, right? And if you have two IGBTs, it will give you 50 rupees into 2 equal to 100 rupees. So can you just see how much is the difference? Can you see it?
Sir, but at the end it's uncontrollable, na,
Why
sir.
is it uncontrolled? This is
Sir,
controlled.
because
This
it
is
is
two
diode.
quadrant control. Huh? So what? You are controlling through the class C chopper, na? You are controlling from the class C chopper, not from the diode side. This is the DC supply, right? DC supply is here,
Sir,
and
100
you are
plus
trying to control the motor side is here. So you're what uncontrolled? The motor is uncontrolled or controlled?
control.
Yeah. So it is drawing its power from the capacitor, right? And the capacitor is charged from the grid side through the rectifier. So it's controlled. In case you want to go for four quadrant chopper, you add 100 rupees more to it. This is for class C chopper. And for this four quadrant chopper, what do you need? Four IGBTs, right? So that would cost you around say 50 rupees into four, 200 rupees, right? So if you go for class C chopper also, then also it's cheaper. If you go for four quadrant also, then also it's cheaper, right? So it's a great thing. And also what? This does not require a ZCD, this circuit. What is this? ZCD is zero crossing detector. So which one seems to be more cheaper?
This diode things.
Huh? Yeah,
This diode.
this configuration is cheaper, right?
Hmm.
So this does not need a ZCD. Zero crossing detector is not required in uncontrolled circuit, because you need not see the zero crossing of the sinusoid and then fire the thyristors, right? And for that thyristor thing, what would be needed? Four thyristors plus ZCD circuit also, and capacitors would also be there. So four thyristors are itself claiming more money than that, right? Do you get the thing now? So which one
Yes, sir.
seems cheaper? So this is cheaper. In the
Yes.
factory, what will be made? The cheapest option
IGBT.
will be made. The cheapest option will be done, right? So that's the thing.
Yes.
Then only you will be buying that. So it can be single phase drive also, three phase drive also, or DC-DC converter. Sorry. So it can be either single phase, three phase, or DC-DC converter drives. Should I go on with today's class, or it's time? Yes, we have time. Okay. So this is the basics of a DC motor separately excited. So what is the instantaneous current that is given by? So what is the equation on the left hand side? On this side, what is the equation of this? Whatever. Okay, so this is the equation for the right hand side. Plus LF into di dt. Is it so? Can you see this picture?
Yes.
So if you have this field coil, and if you attach this VF, then what will happen? What will be the equation? VF is equals to IF RF. RF is what? Plus LF DIF dt. What is F? F stands for the field. So everywhere the suffix is for the field. So field current, field resistance, field inductance, and this is DIF dt, right? So basically the field current is a constant many times, often. So this DIF dt goes to zero. Instantaneous armature current is given by which option? Almost the same thing. So this would be the armature current. This would be the big motor. These are the brushes. So if you are applying a field voltage here, armature voltage here, so what would be that equals to? V armature would be equals to IA RA, right? This would be RA, this would be LA, this would be EA, EB, say, back EMF,
Yes.
plus EB, plus actually the brush drops. Brushes का जो drop है, all the brush voltage drop would be coming here. But the brush drops are in the range of 1 to 2 volts. That is why they are neglected often. Right. So this does not come into the picture. In case you have to go for a very detailed explanation, then you can take hold of this brush drops also, which is around 1 to 2 volts. Right. So this is the armature voltage, armature current, armature resistance, armature inductance, change in armature current, and this is the back EMF, EB. So see, here it is written EG, it's all the same. So here they have used the term Eg, right? Instead of E back. So motor back EMF is given by E back is equals to kV omega IF. So what is kV? So actually it is E back equals to k phi n, right? So what is phi?
Flux.
This E back is equals to k phi n, right? So phi is coming out from where? The field current is giving rise to the field flux phi f.
Flux.
So can we put it like this,
Yes.
right? And n is in RPM here. Can we put something into uh, into omega? So we can change the RPM into radian per second, right? Is it possible? RPM to radian per second. Let's say, let's have a short numerical on it. Say 1 RPM is 1 rotation per minute, right? So is equals to 1 rotation is how much radians? 2 pi.
Yes, sir.
So 1 rotation, if you go completely 1 rotation, so it is 2 pi radian, right? So 2 pi and 1 minute is how much seconds?
60.
60. So this becomes
So,
nice. Perfect, na? So 1 RPM is equals to 2 pi by 60 radian per second. So in the other ways, we can change this n RPM is what? 2 pi by 60 into n radian per second. That's it. Got it? So in order, we can write E back is equals to a big constant, which is consisting of this constant K1 and K2. Say this is K3, right? K3 IF into omega. So can this go, right? So this is good. E back into, right? So one big constant and then IF and omega, right? So this is only written here. So Eg is equals to, that constant is written as kV into omega into IF. So is it okay?
yes, sir.
And then we have torque developed by motor is KT IF IA. So what is this? Let me see, show you. So the torque developed is phi into IA is phi F. That is, the torque is developed due to the Lorentz force, which is basically a combination of this field flux and IA, that is the armature current. So phi F is the field flux, IA is the armature current, right? So phi F into IA. So can we write it like this? Say phi F is produced by IA or IF? Field flux is produced by
IF,
whose
IF,
quantity?
IF.
Field current only, right? So torque is proportional to IF IA,
Yes.
right? So can we write this KT into IF IA, right?
Sir,
So
what
what
is
is
this for K?
KT will be a
Why put?
constant, KT will be a torque constant. See, anything constant, IF IA, if you want to write in terms of equation, what do you include?
Yes.
A constant, right? So here it is in KT, right? Got it? So it will be IF IA, that's it. And then this TD, which is the developed torque, is equals to J into, let me also show it here, T developed torque should be equals to the acceleration part torque J into d omega dt plus b omega plus TL. So what is TL? load torque, right? So what is B omega? V is coefficient of viscous friction. Omega is the speed, right? G is the moment of inertia.
Yeah.
And
Yes.
d omega dt is the acceleration part.
So,
Acceleration or deceleration part. Got it? So this is one is the TD is developed torque and TL is the load torque. So do you get it, the equation, the physical meaning of the equation? TD is the developed torque, then this is the acceleration part, this is the coefficient of
friction.
viscous friction, and this is the speed part, right? This is the load torque. That's it. So see, same is written up here. So solving all these things, what do you get for the speed thing? What is the value of the speed? If you just play with the equations, we'll end up with this thing. So that is the equation of the speed. You have to just keep on playing with the equations until you get this type of equation. Actually, it is this much only. It's up to you just to arrange all the factors in such a way that you get this equation out. That is the equation for speed. Why are you interested in omega? Why are we
सर इससे
interested in
पहले
omega?
वाले स्लाइड में चाहिए तो यस सर
Bolo.
नो सर आई एम टेकिंग स्क्रीनशॉट
Why are you taking screenshot? This is already recorded and I will put it in the drive link, right? So you
बट आई
just
हैव
go
टू
to,
रिवाइज इट दैट्स व्हाई
okay, what you do, I will get this thing into the drive link within 24 hours, right? So after every
ओके सर
24 hours, you can get the full video, then you can do all the things. Right? Okay, so I forgot things. Okay, so why are we interested in this omega thing? And you tell me, why are we interested in omega?
Know the speed characteristics.
Yes, what we all need out of a motor, we need the speed and the torque, right? So speed and torque would together add on to would together multiply to give you the power, right? So we need the speed at which the torque will be delivered. So that's why we are interested in omega. Okay, so we are done with the equation. Now comes the magnetic characteristics, magnetization characteristics. So what is that? It is the graph between IF and E. That is the generated EMF or the back EMF. So what is that essentially? It's essentially a this type of graph. It is actually, if you give an AC voltage, it would start following the BH curve. If you give an AC voltage, it will start following a BH curve. However, because we are not giving AC, we are giving DC and slowly increasing it. That's why it is a graph like this. So where is the linear region? It's up to the this much is the linear. Then comes the knee point. Here, this is called the knee point, where knee point is actually called. It's a point in the BH curve. This part is also like a BH curve only. Here, 50% change in H will cause a 10% change in the B, and B is connected as B equals to mu into H, when mu is the permeability of the material, magnetic permeability. Right. Okay. So I don't want to go to all the deeper things right now. So I'll be stopping here today and we'll continue in the next class. So please tell me if you have any doubts. I'll be turning the slides. Read out. So we'll start the armature voltage control tomorrow. A basic idea is that, the very basic idea is that if you give a motor the supply, if you give the motor a supply, what will happen? It will start to run, right? And if you see, if you turn on this switch, it will start to run. And if you switch off, then what will happen? It will go to stop, not immediately, but after some time, right? So can we give an intermediate voltage? Then we can have a different type of voltage, a speed. Say at 100 volts, it runs at 500 RPM. So that means at 0 volt, it is running at 0 RPM. So
Yes.
does it mean that simple at 50 volts, it should run at in between, say, 250 RPM? It's
Not
quite
so.
good, no?
Yes, sir.
Right? So if you give an intermediate voltage, it will run at an intermediate speed. So that's the very essence of armature control, armature voltage control. It makes sense, right? Yeah. So we will
Yes,
look.
sir.
So we will look to it in the next class, where we will spend more time with that DC motors. Okay. Why are we basically doing with this DC motors right now? Because DC motor is one of the basic units, and if you study it, its characteristics will be seen in other type of motors also, or parts of its characteristics will be seen and can be seen in other types of motors, right? So that's why the DC motor is important. Okay, so any doubts, if you can come up, or else we can stop here for today. Okay, any doubts with the quiz? Okay, so let's meet in the next class.